Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Synopsys with Godwin Maben. We're going to talk today about the challenges of calculating glitch power. Godwin, what is glitch power and when did it become a problem?
So glitch power, before going into power due to, it's the glitches. Generally, designs have toggles. Every signal toggles. Now, how do you separate from a needed toggle or a functional toggle versus redundant toggle? So that's the key. And this redundant toggles, which generally switches, is going to charge and discharge, and that's going to consume power. So since nowadays there are a lot of arithmetic elements in a design, you will see a lot of redundant toggles happening before it settles down. And the amount of power consumed by these redundant non-functional toggle is called glitch power, which we are seeing these days in the range of 20 to 30% of total power. So that's what we call it as glitch power.
Let's take a much closer look.
Sure.
Godwin, what are we looking at?
So let's take a simple circuit, for example, here, a flop and an XOR gate. I drew XOR gate as the most glitchy circuit. So here is the output of the XOR gate is toggling. Now, all of these toggle need not be the real functional toggles. There are some toggles which happens before settling down to actual zero. So this extra toggles, what you see between clock cycle, they are glitches. But eventually, whatever is the delta between these two need to be captured, which is the functional. But before reaching to that functional real value, it toggles. Those are glitches. That is what we are looking at. For example, how do you define glitch? Glitch, if you take a look at this XOR gate, this circuit can absorb the glitch or let go the glitch or propagate the glitch. When does it propagate? When does it absorb? That's the key. There are two inputs to this XOR gate. Both the inputs, if arrival time is T0 for the input 1 and arrival time is T1 for the other input, if the delta between the arrival time between these two signals, T0 plus T1 is less than equal to propagation delay of this gate, then you will not see glitch getting propagated. If T0 plus T1 is greater than equal to propagation delay of XOR gate, you will see a glitch propagated.
Does the problem become more intractable as you move down nodes and as you get more heterogeneous in these designs?
Yes. So let's say we used to use multiplier even at 90 nanometer. We used to use multiplier. What happened was when we moved from, let's say, 16 to 10 to 5 to 4, the distribution between the delays between a gate and the net reversed, meaning now you see 60% of the delay is due to net and 40% used to be gate. The moment the net starts taking control, the arrival time changes. Arrival time, depending upon how I route the nets, irrespective of the function of the gate, the arrival time delta becomes a big challenge. Because of this, what happens is you will see a lot of glitches.
And so your dynamic power density is just significantly higher as you move forward down these designs. Where does that play into this?
So as the dynamic power significantly increases, now if it is a data path oriented design, what we have seen is, for example, multiplier accumulator, which you see in, if you look at any AI chips, AI accelerator, TPUs and whatnot, you will see majority of them doing matrix multiplication, which means multiplier accumulator. A lot of them, 64-bit, 256, 128-bit. There, the percentage of glitch in the total dynamic power is reaching 30, 35%. I've seen cases where 35% of my total power is glitch. For example, security system, you have a lot of CRC generators, ASH generators, security like SHA-256 algorithm, which uses a lot of XOR gates and whatnot. Here, the glitches are 40% of total power. So that's why dynamic power we understand very well. We know we can solve this problem. But glitch is, how do I quantify this? Let's say in all my analysis, I say it's 30%. On silicon, when I put the silicon on the system and measure, it gives me power. I can extract, okay, this is 1 watt, 2 watt, but 30% of 1 watt is glitch. It's very hard to get from silicon. Now, how do I know that what I computed here is right and I'm solving the right problem. That is the first challenge. Now, if you look at dynamic power itself, typically we use typical corner for dynamic power analysis, and we have a setup corner, we have a hold corner, and a typical for dynamic power. Now, just because it's glitch power, I cannot focus on typical because we are looking at arrival time, which means it could be setup, it could be hold. The timing corner is important. So we might have to come up with a new corner for glitch, which could be min-max analysis between setup and hold. And that's where there are many factors. And the other factor is which workload did I pick? Dynamic power is all workload.
You also have thermal effects that come out of this too, right?
Yes. So glitch means, again, with the 30-35% being glitchy and in the dense area. So thermal is one of the junction temperature goes up. So how do I look at thermal impact? What's the impact on thermal due to glitch? In general, we are looking at power and thermal these days because of the density. We are even looking at, earlier days we used to call 100 milliwatts is my target. Nowadays people don't say 100 milliwatts. They say 100 milliwatts for 5 square mm squared. So it's the way we look at power has changed. There's no single number, it's per square millimeter. So that's where thermal is very important, where we look at the density.
Well, it's also looking forward. You've got potentially thermal effects which accelerate aging. They limit the lifespan of the chip.
That's correct. So aging is another factor. So the way I look at aging is, for example, if you look at to reduce power, the common use technique is clock gating. Now, clock gating is not good for aging because it's impacts. Now we are saying that to reduce power, clock gate the design. Now, aging is one of the factor. You need to wiggle the clock once in a while. You cannot shut down the clock permanent. So thermal, power, aging, they're all coming together. We need to look at impact of each of this against each other. That's the challenge here. Which one should I give priority? People say, okay, glitch, I will optimize for glitch. What will happen to my total power? So if my total power goes up, my glitch comes down. No, it can't happen. It should be the other way. So that's where then my total power I reduced, but my aging factor it's not good. Whatever I'm looking at from an aging perspective, which means I need to my dynamic power goes up because I'm less clock gating to take care of aging. And then my power goes up, my thermal, and then EM, then IR drop. So all of these are becoming significant these days. We cannot just look at timing or power alone, the impact of all across nodes.
What factors actually influence glitch?
So and at a higher level, there are 3 main factors which need to be looked at before we quantify this glitch is real. First is, did I pick the right workload? For example, which workload did I, for a mobile processor, for example, I run application A, application 2, B, C, the glitch could be different. So which one do I pick? Do I pick an average of this? Do I pick a small window of this, small window? This is very challenging for any dynamic power. Now, glitch also depends on activity. So workload is first, which again, tools cannot. Today, if you look at in general, tools trying to optimize, they cannot grade your vectors. It depends on architect came up with a vector and told me use this. Tools will optimize, but was that the right thing to do? First one. Next, as I said, activity, more than activity, which corner do I pick to do glitch analysis? Timing corner, setup corner, hold corner, leakage corner, typical corner. These days at a lower geometry, you have some 25 different corners. Whether I take Cmax, Cmin, Rmax, Rmin, all this plays a critical role. I'm not saying we have solved all this problem. So people need to look at what's the right thing to do from a glitch, which corner should I use? It's very critical because here is one example I'm trying to show here is a multiplexer, and a select line of this multiplexer is driven by a heterogeneous fan-out logic here. We are trying to compute the arrival time at this place. Now, depending upon which is active, the arrival time window is this large. So depending upon the signal here arrives here or here or here or here, the glitch could be dependent on all this. Now, if I pick a setup corner, in hold corner, what will happen? So the corner picking is very important because I'm trying to compute glitch here.
How do most companies deal with this? Is it like the 80-20 rule of this is the way it's going to be used by most people, or do they actually go through and calculate everything?
So we did, I personally worked with, for example, 5 nanometer and 3 nanometer. I looked at all these circuits and did a spice analysis, trying to figure out what is the glitch filter here. What do you mean by glitch filter is, as I said, this cell can let go or kill the glitch, either propagate or kill the glitch. Now, XOR gate, what arrival time it will kill, what arrival time it will propagate, I need to know, because in library there is nothing computed. So we typically go understand this and put a global variable saying that glitch rejection is 80-20 or 90-10, or we say 100-100. What this means is, this is a very important factor, because 80-20 means if the arrival time delta between these two is less than 80% of the propagation delay of this, then it will absorb the glitch. If it is greater than this, it will let go the glitch. So you will see a glitch here. Now, similarly, you need to do this, but for every circuit, it is different. For multiplexer, it could be 80-20. For XOR gate, it could be 100-100. So today, there is no way. Glitch is an area where we have just started. So eventually, I believe we will have something in the .lib to explain what pulse need to propagate, what should be stopped based on the spice analysis. So that's a big factor. Yes, there is no standard today, but it's evaluated per node.
That's sort of a brute force approach to it, though, right? Is that the only way to do it?
Today, there's the only way to do is we go for the entire design 80-20 or 100-100. That's the only way, but I'm working with various designers out there trying to figure out what's the right thing to do. Because today, there is a concept called minimum pulse width on a sequential element. We put a minimal pulse width in a .lib. Whereas for a combinatorial logic, there is no concept of minimum pulse width. Maybe we do spice analysis and put a minimum pulse width, then it'll be easy to measure, easy to optimize. But is that the right thing to do? We are not sure. We are evaluating all of this.
Who's getting hit by this? Is it the big processor makers? Is it the SoC guys?
Mostly processor and guys who are purely into compute, whether it's a processor, heavy compute, which is the most of AI accelerators today, all compute heavy. They are the ones who are getting hit by this because they need to fix this before the total power just explodes.
Corners have been going up in almost all the complex designs right now. There's hundreds of them that are critical versus go back years ago, it was what, 10, 15 corners that you had to worry about? How many of them are tied into power now?
Power, typically, if you look at it, a typical corner and a temperature inversion corner for leakage. That's what we were looking at so far. Now with the glitch, I think there's going to be a lot more corners because it's related to timing and arrival time. It's all glitches, even though we talk about power, it's all about arrival time, which means timing corner becomes critical. I pick setup. In setup, which one? Cmax, Cmin, all parasitics plays a big role. And today, everybody has a fixed methodology to define corners for timing sign-off. Now, power was always, everybody used to say only 2 corners. Typical, temperature inversion. That's going to change going forward. For glitch, I need to add few more corners, which I need to steal from timing corners and introduce glitch corner.
Does a lot of this depend upon how consistent the computing is? So you think about utilization in a data center, for example. You typically want it up around 60, 70, 80%. A lot of it's been running at 10, 15, 20% in the past. As you start raising that percentage, does that now increase the glitch potential?
It could increase the glitch potential also. But now, if I take this problem, power is all about, if I shift back, if I look at energy, so most of the cases people are looking at energy. Now I can reduce the energy by going multi-cores, right? Instead of getting the work done fast and sitting idle, now I distribute the work at half the frequency across different cores, then I can control that. Yes, with the compute going up, glitch will go up, but there are ways to control that.
And you control that through, I mean, that's assuming you have parallelization and virtualization as well, right?
That's correct. And scheduling. Software need to be very efficient in scheduling, knowing which hardware is idle, which is not idle. How do I schedule them right? That's very important. And dynamic voltage and frequency scaling, which is all about multiply in one clock cycle, let's say at 4 gigahertz. What do I do? Oh, I multiplied in 4 gigahertz, but I'm waiting for some other data for next 200 clock cycle. Instead, I can multiply this in 2 gigahertz and wait. So that's the challenge. And if I move from 4 gigahertz multiplication to 2 gigahertz multiplication, I don't need to operate at zero point 0.8 volts anymore. I can operate at 0.6, which means my glitch power, everything comes down.
That's assuming you can parallelize the operation that you're trying to do as well. The challenge now is what happens when things are not moving exactly the same way. Say you have glitches in some areas and not others. So now you have uneven compute, right?
Uh, so you're right, but uneven compute, as long as the computation is done in a given time period interval. So let's say 5 clock cycle, I need to compute some function. As long as you finish, that's a good metric to look at. In between that 5 clock cycle is where there is unevenness. So which means potentially the glitch could be a lot more when there is unevenness. So that's where it's.
And does it magnify now as you start getting into heterogeneous designs where you have computing running through lots of different elements?
Yes, so it just amplifies significantly because of that.
So then on top of that, you have to layer in, because these are getting much more sensitive to variations here. Now you have to measure in all sorts of variations, right?
That's correct. So variation is key also, because at the end of the day, glitch is all about arrival time, which means variation plays a big role, because I'm trying to compute this window. And if I add plus or minus, let's say, how do I tackle variation? Typically, people use D rates to model variation. Now, in this case, that's a very complex formula to extract to accommodate D rate model variation through D rate, and then look at the arrival time window. It becomes more complex.
There's a security element in here too, isn't there? There's a potential for hacking into this by virtue of the glitches.
Yes, so that's also one factor, because people use heat signatures to do all of this, and you could use this to hack into a system. So there has to be a security aspect. That's where the distinction between functional toggle, non-functional toggle. Now, as an hacker, I can get into a non-functional toggle area and use that to do something.
So given the complexity of this, what's the best place to solve the glitch?
Architecture level is the best place to solve the glitch. The reason being parallel architecture versus a ripple architecture. For example, I talk more about computation, multiplier, adder. I could go with a parallel multiplication architecture, or I could go a CSA architecture. Now, parallel is better from a glitch perspective, whereas if I have a ripple structure, it's going to be very glitchy. So if you look at designers, typically they don't look at glitch, they look at performance. And then for this, it's a low performance, I'll go with the carry save ahead adder, which may not be as good as some parallel architecture. So that's the first place to solve the glitch. Now, as the design is frozen and the RTL coding is done, tools can play a role, but the amount of glitch the tools can fix is going to be very small, because what can they do? They cannot take your ripple structure and convert it into parallel, because that's a major change. Functionally, you have to revalidate it. All we can do in the tool is, how do I balance these two pins so that the glitches don't get propagated, which is nothing but delay balancing. It by itself is a very complex problem. Just to get a clock skew correct till today, everybody are struggling to get zero skew. Now, clocks are possibly thousands, and the number of clock pins may be 100,000. Now, if I look at the input of every AND gate and balance, that is millions of bits. It's impossible to solve. So the more you get into towards place and route, it's very difficult to solve. Yes, we can get 2%, 3%, 5%, but if I want to kill 30% glitch, no, it's not possible in the tool side.
So do the design tools have to be completely redone in order to deal with this, or is it just one more element that you have to think about as you're doing it?
Uh, One more element as we do it in the place and route segment. But if you move towards the front end part, we might have to look at the architectural selection as a new thing, glitch based architectural selection. That's a brand new thing. Today it doesn't exist. Everybody are working towards it.
So if you're doing pathfinding, this is something that has to enter into that picture, right?
That's correct.
So if you actually come up with a number that states 30% in glitch, what happens in silicon? Can you actually measure that?
So that is a very known problem till today. Typically, when I go look at the silicon and I say 1 watt, this average is. Now, I don't know on silicon, I can tell that 30% is due to glitch or 50%. It's very difficult. Now, after taping out many chips, people have figured out there is a methodology on how to get what percentage of total power is glitch. I can do a frequency sweep. You need to come up with a new methodology to quantify what percentage is glitch. Yes, people have done, but these are all new problems which we started dealing with a year back. Now we are still new. There are few silicons out. They have figured out a methodology. I believe we can, but it is not a straightforward measuring V and I. Power is just measure V and I, you get power. Glitch is not that simple.
Godwin Maben, as always, thanks for a really great explanation.
Thank you, and you're most welcome.